Hello and welcome to the second lecture video for Chapter 7 from the Physics of Everyday Phenomenon by Griffith, 10th edition. Here we're talking about recoil because Chapter 7 is all about momentum. In the first lecture video, which covered the first two sections of this chapter, so that was sections 6.1 and 6.2 covering momentum and impulse, important definitions, and then the fact that momentum is a conserved quantity like energy, the law of conservation of momentum, all covered in that lecture, okay? Or those sections and that lecture video. Now, in this lecture video, my goal is to cover the last three sections because they definitely group together, all right? You can see that section 5 is just collisions at an angle, which is just a small subset that we don't do much with mathematically of the more important elastic and inelastic collisions, because those ones can be one-dimensional, which is the type of problem that we can really kind of handle in this class, right? That's appropriate to the level of the class. Okay, so that means that we're picking up, though, on where we left off on section 7.3. All right, so 7.3 is all about recoil. Now, by the way, in the first lecture video, I spent a long time justifying momentum. Why the heck do we care? So I'm going to assume that you know that momentum is just one of those important building blocks of physics, okay? It's just so darn helpful, okay? Now, what do we got? Well, looking at recoil, I mentioned before that it's all about, shooting cannons and high-speed phenomenon, but it could just be simply two people pushing off of each other with ice skates, because this is a system where there's no significant external forces during the pushing. So even though the pushing may not happen within microseconds or something, they have to actually spend a little bit of, contact time, some fraction of a second, actually pushing their palms together to get a good final speed once they separate. Regardless, there's not going to be really any external force because of the very low friction in the system. So if you see a conservation of momentum problem that might not be an explosion or a firecracker or a gun being fired or a cannon being fired, then it's probably going to involve ice or some very low friction, because we really need that condition to be met. Because remember, conservation of momentum, incredibly big idea, incredibly useful and important idea, but it only works if the sum of external forces is zero. We need the system to have no external forces acting on it. It can have internal forces, like the force between the two people here, okay? But no external forces, because the system is the two of them, all right? So when they push off of each other, all right, that's this case, right? That's what we use conservation of momentum for. This is a perfect example of using conservation of momentum. Now it's recoil because there is some initial force, okay, which is also an initial release of energy, that force was applied over some time. The product of the force and the time is the impulse. You might even be given in the impulse value in a problem like this, or maybe that's just what you know. But then afterwards, the purpose of quantifying the system is that we need to know what's going to happen, either because we just want to measure it or because we want to predict it, okay? So if we know that they give each other a certain force, then we know that they're going to have a certain final velocity. And furthermore, we know that they're going to have a certain net momentum. Okay, what's going to be the net momentum? Well, the net momentum actually has to be zero. Why do we know it has to be zero? Because they both started at rest, and the entire system is the two people. All right, so when they push off of each other, the final momentum still needs to be zero. So recoil isn't anything new, it's just conservation of momentum. But it's a nice particular case of conservation of momentum where we always know that the initial velocity is zero, okay? So that's really where recoil kind of shines, is that idea that it's some system that starts off from zero, and then afterwards, two things that weren't moving are moving. Now, one thing that is actually in this section on recoil, which has nothing to do with recoil exactly, are rockets, because rockets are going to be in motion the whole time we're going to use momentum to quantify them. But we kind of need to squeeze it in there anyway. And the focus on here is really just to show that momentum explains the motion of a rocket, because a rocket pushes on the gas pushes on the rocket. That's a force pair, right? But that also causes the rocket to, well, get pushed on, which means it can accelerate, which means that it has some change in momentum, okay? Now, this is a continual process with the change in momentum. So it's really a situation where you might say, well, isn't this better for acceleration? Isn't this the kind of like constant force, constant acceleration that, we wouldn't use momentum for? But there's a reason that I hinted at before in the first video, I mean, I talked about it briefly, I should say, I didn't hint at it, but I briefly mentioned it among many other ideas. So if you have watched the video and you forgot me mentioning rockets, you're forgiven. But regardless, rockets are a particularly good case of using conservation momentum, but not for many of the reasons that I've been focusing on. They don't happen fast and so on, okay? But they're gonna be on the slide, so let's get there. So, a couple questions to start off on recoil and get back to where, kind of grounding this idea. Why does a shotgun slam against your shoulder when you fired it, okay? Right, sometimes painfully. Why? Because of conservation of momentum, right? Bullet moves out with very great momentum. The initial total momentum of the bullet and gun was 0, which means the gun needs to have the exact opposite momentum. Same in magnitude, opposite in direction, because remember, momentum is a vector, okay? It's that p vector, all right? We see here that little p, the p vector shown here in purple, right? For that case, think, football players crashing together. So how can a rocket accelerate an empty space when there's nothing to push off of except itself, right? Because you might be like, oh, well, you can have a rocket in the atmosphere, but you can actually put a rocket in the vacuum of space where there's nothing to push off of, okay? And it doesn't need anything to push off of external to itself. It can create a process where it leaves something behind, okay? So cool idea about rockets, especially when they're in space and there's nothing to push off of. So going back to our skaters, so we have two skaters of different mass that prepare to push off against one another, okay? So which one will gain the larger velocity? The more massive one, the less massive one, or will they both have equal but opposite velocities? Is the velocity conserved? Think about your answer. All right, I'm gonna show the answer now, okay? The less massive one. Why? Because the two momentums, right, that, say we call this person 1 maybe, right? So her momentum is going to be the product of her mass and her velocity after the push, all right? This child over here, their momentum is going to be the product of their mass and their velocity after the push. We know that those two momentums have to be equal to each other, the product of the woman and the child. Why? Because the initial momentum was 0. So now we have to have their two opposite direction momentums summed to 0. Conservation says it, okay? What's cool though is that if you forget that this comes from conservation, this holds true for any recoil. Because any recoil, any situation where the object started at rest, this will always be the case. Two objects that started at rest, they're both moving after something happens, then this equation will always be true, right? For object 1 and object 2, all right? Now, as we see, right, it's definitely not the velocity that's conserved. I ask that because it's not at all. Sometimes people think conservation of momentum also means conservation of velocity. That is not the case. It's very rare for velocity to get, conserved, right? For the objects to have the same velocity coming in, both objects in a two-body collision, and then they both have the same velocity coming out. There's that's like a really special case that's really particular. It almost always changes, okay? Even the sum of all the velocities before and the sum of the velocities afterwards, that also changes. Because think about here, right? The sum of the initial velocities was 0. The sum of the final velocities is just v1 plus v2, right? Now, yeah, one's a vector and one's not, but the sum is still not 0, right? If we look at the picture, we can clearly see, right, if we were to sum v1 and v2 is a large positive value because it's pointing in the, towards the right, the typical positive direction. V1 is a smaller negative value, so v2 plus v1 is a positive non-zero value, okay? Definitely not conserved. But what is that product, right? The m times v1, m1 times v1 equals m2 times v2, all right? So both must move at the same momentum every time with recoil, all right? Opposite directions, right? So as vectors, p2 equals negative p1, okay? When added together, the total final momentum of the system is then 0 because it was conserved, no external forces, and it started at 0, okay? The total momentum of the system. What's the system? The two people, the two skaters, okay? The ice is not part of the system. The air is not part of the system. The system is just the two people. And we're assuming that those things, like the ice and the air, don't apply any significant external forces to our system, the two people. There we go. Conservation of momentum is met, okay? So, since momentum is mass times velocity, right? Remember that is the formula, P for momentum, okay? Equals mv. The skater with the smaller mass must have the larger velocity, okay? And we can solve for what those values are. The lighter object attains the larger velocity to equalize the magnitudes of the momentum of the two objects, okay? The total momentum of the system is conserved and does not change. Recoil is a great example of a conservation of momentum problem. Okay? But when you think of recoil, you probably don't think of ice skaters. You think of something more like a gun, or maybe you think of microscopic spores being launched. When I was a graduate student, I actually studied the physics of fungi, and one of the things that we looked at was these amazing microscopic fungi that can achieve some of the greatest accelerations in the natural world, up to about 100,000, even 300,000 times gravitational acceleration. That might sound like, wait, that can't be right. Well, that's actually, it is right, and it's not that it's fast in the animal world. It's definitely basically the fastest, not animal world, but the entire natural kingdoms, right? Fungi being their own kingdom, separate from Animalia. But my point is that, yeah, it's fast, but even like insects, they'll move at thousands of G, because as you make things more and more microscopic, they inherently have greater and greater accelerations. So acceleration scales up as size scales down. All right, that's a discussion for another day. Check out this video. So real fast, this is in fact a fungi, probably what you don't think about, but this is like on like a petri dish, so it's zoomed in. This is actually the reproductive organ of the fungi. This is a sac here that grows on a stalk, and within is a pressurized water. Fungi are able to create really high pressures because they can create like stronger cell walls than animal cell walls. They're not like plant cell walls, not quite, but they actually they can make use of chitin. Whereas we don't make use of chitin. Chitin is the stuff that like insects have in exoskeletons. So it's kind of interesting, right, that they're using those chitin in their cell walls. Point is, they can build up very high pressure. The spore with the unique DNA to actually reproduce, much like a seed, is right here at the end. All right, and it's sealed on. It grew with the pressurized sac, but here when the spore is ready to be propagated, then this connection between them is going to tear because the pressure is going to become so great. Okay, that's going to release the spore, right? Because there was a force pushing on it the whole way, but it couldn't go anywhere because it was attached. Well, what happens the minute that attachment breaks? Well, just going back to Newton's laws, you're going to get a single force, so then you're going to have a acceleration. So you definitely have an acceleration. It's that the force is going to be applied over a very short time. After that, it's just a matter of basically a projectile, a free fall situation, although not quite, because the drag is actually not negligible for small things, but again, not doesn't matter. But afterwards, regardless, it wouldn't be the impulse anymore. The impulse is just the force over that short period of time. Right? This is very high speed camera photography you're about to see. But this then, that means that the momentum must be conserved. And if the spore accelerated towards, the right, then the stalk that was, holding the pressurized fluid, it's going to have to kick back to the left. That's recoil in the natural world. All right. We could come up with that with Newton's third law, certainly, but here we're seeing it with conservation of momentum. The system started with zero momentum, the system being the stalk, pressurized, sac here, and spore. That's the whole system. All right. The system's going to end with zero momentum. Check it out. Recoil. But what goes faster? That shows it so clear right there, right? The spore. Why is the spore achieving the greater velocity than the stalk? Because it's less massive. Right? Natural canon. It's a lot of force. Especially because, these things are only about, this whole distance here is about 1/5 of a millimeter from base of the stalk to the spore. 1/5 of a millimeter. Look at that thing. It's speculated that spores like this, and there's many other examples, have evolved such incredibly sophisticated launching mechanisms because there was incredible competition within the natural world. And where do we see some of the most innovative evolutions? Where there's the greatest competition. And because it turns out that one way that spores like this, the ones that have evolved the most unique processes, they're competing over what? the dung of herbivores, like cow poop, right? Like a big cow patty, because it's just such a highly concentrated bit of nutrients. There's herbivores in lots of, grassy habitats over the world, and that's just been like this, highly sought after environment for colonizers, and spores are some of those first colonizers along with bacteria. And often there's going to be a competition between fungi and bacteria. Okay? So again, more classically, right, the thing we think of more is more like guns, right? We don't think of, spore stalks as the perfect example of recoil, right? At least maybe you don't. I certainly do. But again, going back to the gun, right? So we have a gun, right? The explosion of the powder in this old-fashioned gun is going to cause the shot to move very rapidly forward because the shot has very little mass, especially compared to the entire, musket or entire gun. The gun is free to move, and it will, and it's going to recoil backwards with the exact same momentum in magnitude, opposite in direction, as the shot, okay? But that will result in a much smaller velocity for the rifle. Now, it's still enough velocity, as the original slide pointed out, to be noticeable. It can hurt you, right, the recoil of a gun, right? But thank goodness it's not the velocity of the bullet, right? So even though the mass of the shot is small, its momentum is large due to its very large velocity, maybe, a couple hundred meters per second. The shotgun recoils with momentum equal in magnitude to the momentum of the shot, okay, because that's the way we sum up to zero momentum, conserving it. The recoil velocity of the shotgun will be smaller than the shot's velocity because the shotgun has more mass, a lot more, right? But it still can be a noticeable amount, a couple meters per second. So if the shotgun, on the other hand, is held firmly against your shoulder, it won't hurt as much. Why is that? Well, because if you don't create a gap between the gun and your shoulder, then you've then made you and the gun one object. Now the system isn't the gun and the shot. The system is you holding the gun and the shot. You've included yourself in the system. There's no chance for the gun to move independently of you. Well, now you've added your mass. So that's going to mean that the overall velocity is smaller. It might make you more likely to stumble, right? But it's going to make it much less likely for the gun to slap into you, okay? Because you pushed it up against yourself, all right? So here's the idea, right? If you think of the system as just the shotgun and the pellets, then your shoulder applies a strong external force to the system, okay? Or you just think of including your body in that system. Since conservation of momentum requires the external force to be zero, the momentum of the system is not conserved, right? So, in that sense, you might be like, oh, well, then it's not a good problem for momentum. But like I said, you don't have to think of it that way. You don't have to think of your shoulder as an external force to the system. Instead, just think of including yourself in the system, right? So if you think of a system as including yourself, okay, with your shoulder against the shotgun as just being like, part of one solid object, then the momentum is still conserved because all the forces involved are internal to the system. See that key difference, external and internal forces. All right, pay attention to that because that's an important idea. Don't gloss over it. Make sure you're clear on what that means, okay? So accept possible friction between your feet and the earth, right? But we're going to ignore that. We're going to idealize the system as we do. So with your mass added to the system, the recoil velocity is a lot smaller, okay? All right. So the rocket, right? So the rocket is not that case that I've been highlighting is kind of easy to wrap your head around, where the momentum started at zero because everything was at rest, then something happened like, firing a gun or launching a cannon or whatever, right? Or, the spore getting released. And then two things are in motion that were both initially at rest. So therefore the momentum was zero before and it's going to be zero afterwards, right? There we go, okay? But with a rocket that's moving through space, it was never zero. The rocket was in motion no matter when you look at it, right? Because we're not talking about the launch, okay? We're not talking about the launch because the launch, it's pretty clear what happens in the launch. The rocket, pushes with the gas pushes on the ground. We can kind of think of that force coming right back up into the rocket from the ground. But what about when there's no ground, right? Because it's not like the gas pushing on the atmosphere is where is going to be where the force comes back to the rocket. No, it's the idea that we now have, we have a system where the rocket is the entire system, okay? So that means that what we're looking at here is we could look at there's two ways to do it. We could look at the rocket as the entire system and exclude the gas. In that case, when the gas goes backwards, think about what happens. The rocket pushes the gas out of some exhaust nozzle. Hear that word? It pushed the gas. What does Newton's third law tells us? Well, if you push on something, that something pushes back. So if the rocket pushes on the gas, forces it out of that exhaust nozzle, and that's why you want to have like a small nozzle so you can really force it out at high speed, okay? It's not just enough to blow things up. You want to, direct that force, okay? So, because, these are all explosion-based, projectile or explosion-based fuels. So when that gas is getting forced out of that nozzle, right, as I said, rocket pushes on the gas pushes back on the rocket. Newton's third law definitely tells you that there's an external force acting on the rocket that's going to keep the rocket accelerating. That's fine, right? But the problem is that if we wanted to actually work that out numerically, then how do we deal with the fact that as that gas gets pushed away, that is significantly changing the mass of the rocket? Because a big part of the original mass of the rocket was all the fuel that's getting spent. Well, it turns out that's one of the reasons we really like to use momentum for the rocket. Because if we include, I almost said exclude, but if we include the gas, now we have a system that consists of the gas exhaust and the rocket. Those two things are moving in opposite directions. And their change has to be equal to 0. Why do we know their change has to be equal to 0? Well, because there's no external force. Think about it, right? Maybe like, what about gravity or something? Well, yeah, maybe, right? But not over like a short distance. It wouldn't matter, right? And and so especially if this rocket's in deep space and there's relatively small forces of gravity, then over some reasonable distance, we wouldn't care about those external forces. They wouldn't significantly affect the motion of the rocket. Instead, it's going to be as if there's nothing around it. It's truly just these two things, the exhaust and the metal rocket itself, and that two object system is entirely isolated and has no external forces acting on it. Okay? That means that momentum is definitely conserved. Okay? Now it didn't start at 0, but we don't need it to start at 0. That is, the momentum didn't start at 0. We just need it to not change. So that's why you see a delta. So the change in the momentum of the rocket fuel, the exhaust, right? That's going to be exactly equal to the equal magnitude, opposite in sign, hence the negative, to the change in momentum of the rocket. Okay? So whatever change one experiences, so does the other. Okay? So that's great. Right? We can still come at it with Newton's third law, but what's so cool, which we won't cover in this class, is that when you take the momentum approach to working with this, you are already set up to deal with the fact that m itself is time dependent. So you've got some sort of fact that as you continue to, change your momentum, which means you speed up, then you can actually exactly figure out how the fact that the rocket is gradually getting lighter means that it speeds up more than it would otherwise. Because it's actually an advantage of rockets. It's a built-in advantage that they have to use up their fuel to go somewhere, because that means they get lighter as they go. But it's also a built-in disadvantage, because one thing people say in astronomical engineering, or aeronautical engineering, is that you have to give something up to go somewhere. Now, when you build a plane, yeah, you have to burn fuel, right? But you can just generate lift force, with a wing. There's no generating forces because there's no forces around to push off of. There's no atmosphere, right, when you're in space. So the only way to get somewhere is to push off of something, okay? And to push off of something, you have to leave that thing behind, because if you didn't leave it behind, then it's not an external force anymore. So the rocket has to use up its fuel to literally push off of it to keep it going. That means that eventually it will use it all up, right? So you always have to leave something behind to accelerate in space. And remember, acceleration is also turning and slowing down. So you might be like, well, just don't accelerate so much. But you have to do a lot of accelerating to actually, say, navigate and eventually decelerate when you get somewhere. Okay, so now let's talk about the collisions, all right? We knew there was going to be collisions. I mentioned that momentum is very well suited to the study of collisions. All right, and we can see here, right, in section 7.4, elastic and inelastic collisions. There's a few subtypes, right, besides just those two terms, which of course we'll define. There's perfectly inelastic, all right? Then there's going to be perfectly elastic and then partially inelastic. So those are the real three cases, okay? And we should think of them all as one-dimensional at first, and then eventually we'll consider a two-dimensional case, okay? So collisions, great, right? One of the big things you can do with momentum. We did see a collision in the first lecture for the first half of this chapter when we looked at the football players, okay? So this shown here are two examples of collisions, and they're collisions in a simple case because they're colliding with this wall, and the wall is unmovable. So this is the collision where momentum is definitely not conserved, because there's no way to reconcile the fact that the wall can't move, right? Because that means inevitably you're going to end up with, a net change in the momentum, right? If you include the wall, then you're like, okay, well, then we have to actually measure the movement of the wall, right? Because there has to be some give, right? But how could you measure such a tiny velocity? You can't, So you're stuck with the case that from the perspective of looking just at the ball, there is an external force, the normal force from the wall. So it's not a conservation of momentum case, okay? It's actually a change in momentum. And sometimes that's okay. Sometimes we don't need to just focus on cases where momentum is conserved. Sometimes we can use momentum when it's not, to talk about an actual, net change in momentum. Okay? But here the key isn't even so much that the momentum is changing. We actually highlighted that earlier in the lecture. It's the fact that we have the case where the tennis ball bounces back, it ricochets back with no loss in energy. Okay? We know it's no loss in energy because the initial velocity and the final velocity are precisely equal to each other. Now this is shown as slightly two-dimensional. That's just for being able to clearly see all the arrows and the labels. You should think of this as one-dimensional. Hits the wall, bounces right back the way it came. Okay? Now a perfectly inelastic collision is where two things that were unique, that weren't part of each other, after the collision are. Okay? That's actually what we saw with the football players, referred to the previous lecture video, because when they collided, different masses and different velocities and different initial momentums, and the momentum was conserved there, we had a case where they stuck together, essentially, the one player held on together. That was an inelastic collision, specifically a perfectly inelastic collision, because they were one thing after the collision. Okay? So, right? What's the difference between them? Well, I started talking about the difference. I haven't highlighted the difference of a partially inelastic. Suffice to say, it's when you don't quite stick together, okay? And then what about energy conservation? Because that's actually a key part of this. Because elastic collisions are collisions where energy is conserved, and they are the only collisions where energy is conserved. Any other collision, whether it's a perfectly inelastic or a partially inelastic, loses energy, okay? That's the key thing. Because there was the energy, the mechanical energy got transformed to some other form of energy like chemical, electromagnetic, heat, or something, okay? All right, so let's then look at the simplest case, which is the case where energy is not conserved. You might think, well, shouldn't energy being conserved, isn't that the more elegant, simple case? No, for a number of reasons. One reason is actually more difficult to solve because you can have more independent variables to solve for. And it's not quite as intuitive or simple, all right? So we'll get there though. So a collision in which the objects stick together after the collision, that's the criteria, okay? As long as that is met, all right, then you have what's known as a perfectly inelastic collision. They can't bounce off of each other after the collision, okay? There's no bouncing at all right? And we know that the total momentum before the collision, all right? If we know the total momentum before the collision, we can calculate it afterwards, okay? All right? And what's it going to be, right? Well, the total momentum before the collision is going to have to equal the total momentum after. Because are there any external forces in the system? No. There's an internal force, the force when this car 5 comes together and joins with the rest of the cars. That's an internal force because the entire system is the train. Okay? All 5 cars is the system. So no external forces because we're assuming no friction between the tires and the track and no resistance from the air. Okay? So the football players who stay together after the colliding, right? Coupling railroad cars, common examples. Also like clay sticking to something, right? That'd be a case. Or shooting a bullet into a piece of wood. Those are other cases of perfectly inelastic collisions. So let's run some numbers. So 4 railroad cars, all with the same mass of 20,000 kilograms, so 20,000 each, so net of 80, sit on a track. A 5th car of identical mass, so another 20, approaches them with a velocity of 15 meters per second. Remember, the 4 here are sitting. That means they're at rest. So their initial velocity is 0, which means their initial momentum is 0. Okay? This car collides and couples with the other 4 cars. What is the initial momentum of the system? Okay? So don't even worry about the after effects of the collision because we know momentum is going to be conserved. So if we can calculate the initial momentum, we're going to be in a great place to calculate something like the final velocity once all the cars are coupled together. So to find the initial momentum, remember that these 4 cars do not contribute, right? Even though they could, they don't, okay? And the only car that actually has non-zero momentum is car 5. So it's just going to be 20,000 times 15 meters per second. This is the entire, as you can see in the label, the entire initial momentum of the system, okay? So what's 20,000 times 15? I probably gave away too much, right? But do the calculation. All right, it's 300,000 kilogram meters per second, or 300,000 Newton seconds. Okay, that's the initial momentum of the entire system. Yes, it's also the momentum of just that one car, but that's because the other cars were at rest. Okay, so now they are stick together. They're all going to move as one. Okay, there's still no external forces. Momentum is conserved. And the question is, what is the velocity of the 5 coupled cars after the collision? Okay, so if the momentum is conserved, that means that this value of 300,000 still holds. We're going to have a total mass of 20 times 5, or 100,000 kilograms. So the total mass is 100,000 kilograms, and the momentum is an unchanged 300,000 kilogram meters per second. Then what's the final velocity? Yep, 3 meters per second, right? So what we did here is we acknowledge that P final has to equal P initial. That's how we know what P final is, okay? So then we just say then that V final is just going to be P final divided by M total, or 300,000 kilogram meters per second divided by 100,000 kilograms. So after they're all coupled together, they're moving at 3 meters per second, right? Did they slow down? Sure, right? The original car, when it was moving on its own, was moving much faster at 15 meters per second, like highway speeds. Afterwards, they're moving fairly slowly, right? Still pretty fast. You wouldn't want to be in their way. And the reason that they slow down is because there's a lot more mass. That's what we expect, right? But we can actually directly quantify it, all right? With just a little bit of reasonable, ignoring of, like friction or anything, because they wouldn't be that significant here. Okay, so if the kinetic energy is the kinetic energy after the railroad cars collide equal to the original kinetic energy of car 5? Okay, was kinetic energy conserved? Yeah, I got your answer. I'd said this before. Definitely not, right? There's actually a huge loss in kinetic energy. So any type of collision that isn't the elastic type, which is the type of collision that by definition conserves energy, which is hard to do in practice, right? Well, all the other collision types lose energy. And the type of collision that loses the most energy is the fully inelastic. That's the case where you have, in general, the most loss of energy. You can have special cases of mass combinations where you can have, also even more energy lost. No, actually, the most you can possibly have lost is going to be 100%, where you got two objects, equal mass, equal magnitude, velocity, opposite direction velocity vectors crashing together, and then their final momentum is going to, their final velocity, I should say, is going to be 0. So the final kinetic energy is going to be 0. All right? Whereas their initial kinetic energy was definitely not 0. That's the maximum amount of loss you can have. And what type of collision is that? That's going to be one of these ones, a perfectly inelastic collision. All right? Now, in partially inelastic collisions, that's where things bounce off of each other, but some energy is lost. All right, little bit more impractical to actually solve for, even in my algebra-based kind of like more in-depth classes that you use different textbooks. We would still usually kind of just give you that value because often you have otherwise too many unknowns to solve for. But look, you can actually look at the values. So if you take the form of kinetic energy, which is 1/2 mv squared, and you look at the initial total kinetic energy, the initial total kinetic energy is just going to be that of car 5 because car 5 is the only one in motion. So it's just going to be 1/2 mass of car 5 times the velocity of car 5 squared. So 1/2 times 20,000 kilograms times 15 meters per second squared. Squaring makes a big difference, right? Because after all, we went from 15 to 3, in terms of the magnitude of the velocity. Squaring 15 and squaring 3 are very different values, right? So here we see, right, that we then end up with a total initial kinetic energy of the system of 2,200 kilojoules. So that's essentially 2,250,000 joules, right? That would be converted over. Continuing on with the final kinetic energy, we have everything we know. Well, we have everything we know. We have everything we need to solve for it. We know that the total mass is 100,000, and we solve for the total velocity using conservation of momentum. So it would be a two-step process. If someone asks you for the final kinetic energy after the cars coupled together, well, then you would find the final velocity using conservation of momentum. Then you'd plug that final velocity in, like they're doing here, to find the final kinetic energy. What's the final kinetic energy? Only 450 kilojoules, or 450,000 joules. Big loss, right? Our energy went down by, over 75%, right? Huge loss in energy. So, elastic and inelastic collisions. Energy is not conserved in perfectly inelastic collisions. In fact, a lot of energy is lost. If the objects bounce apart instead of sticking together, then the collision is going to either be elastic, that special case where energy is conserved, or partially inelastic, which is they didn't stick together, so they're not the perfectly inelastic case, but some energy is lost. That's the difference between these two cases where there is bouncing. Okay, so the greatest portion of energy is lost in the perfectly inelastic collision. I almost started to say otherwise a minute ago, and then I'm like, oh no, it is that case where they come together, right? And then also in general, it doesn't, even if you had different combinations of mass and velocity, that's always going to be your case where the relative amount of energy is lost. The greatest relative amount of energy is lost. Now this is just a bunch of different cases here. So a wall of text, right? A ball bouncing off a floor or a wall with no decrease in the magnitude of its velocity is an elastic collision, okay? Which is an idealized case. It doesn't really happen, right? The kinetic energy does not decrease. It's perfectly conserved. No energy has been lost. A ball sticking to the wall is a perfectly inelastic collision. Now, most collisions involve some energy loss, right? Even if they don't stick, right? We noticed that, right? When we talked about the bouncy ball does not return to the same height, no matter how good it is, right? There's no way, you can't even really get close to it. That's because there's gonna be a significant amount of energy lost, especially in the impact, right? All that heat that's getting generated, sound energy, okay? A bunch of energy that's being quote unquote lost, but really just transformed from mechanical energy into other forms of energy, which they point out as being less useful, and that's true, right? Heat energy, by its very nature, is more entropic than organized mechanical energy, and the second law of thermodynamics tells us that we cannot 100% convert that heat energy back to mechanical energy, but we sure could have converted 100% of our mechanical energy into heat energy. So you can go one way, but not the other, okay? No perfect heat engines. So the billiard balls are often taken as that perfect case of an elastic collision. Are real billiard balls perfectly elastic? All right, is energy truly conserved? No, right? But close enough, right? So the simplest case, we have a head-on collision between the white cue ball and the 11 ball initially at rest. Okay, so we're assuming no rotation, right? So otherwise, we have to deal with conservation of angular momentum as well. So we're ignoring spin or saying that's not a factor. And then we're saying that the 11 ball's final momentum is equal to the cue ball's initial momentum, okay? Momentum is conserved, and the 11 ball also has a final kinetic energy equal to the cue ball's initial kinetic energy. Energy is conserved, okay? So in this case, where one ball was at rest, the other ball hit it head on, they actually trade places, okay? Because the 11 ball picks up the exact amount of kinetic energy that the cue ball had. Since they're identical masses, that means that it's going to pick up, its same velocity as well, right? So the cue ball is going to go from some initial velocity to 0. The 11 ball is going to go from its initial velocity of 0 to what was the initial velocity of the cue ball and is its final velocity, okay? And that comes directly out of conserving both momentum, so P1 equals P2, and kinetic energy. And the picture implies it, because you can see the only one moving after the collision, where P2 is shown, is the 11, right, with the band, with the stripe. The cue ball would be at rest at this point. This only happens because they have equal mass. Now you could make one slightly more massive and still have one initially at rest and then solve for the final velocities in that case. You can make them both in motion and solve for the final velocities. You can make them both in motion and different masses and solve for the final velocities, because with these two equations you have what are called two independent equations. So algebraically you can solve for two unknowns. What are the two unknowns you would solve for? The two final velocities. Pretty cool, right? All you need, you know the masses, and you know both the initial velocities. In this case, right, some non-zero initial velocity of the cue ball and 0 for the 11. Now, something called Newton's cradle is another example of that. All right, I'll let you read this slide on your own. Kind of interesting to refer to after the fact, but it's just another case. Okay, so the last thing we'll talk about is collisions at an angle. Okay, now this is neat because it's a throwback to something I talked about when we quantified motion way back in chapter 2 or 3. Chapter 2 we had vectors. Chapter 3 talked more about vector addition. That's what we're doing here. We're doing vector addition again. So please review vector addition if you need to. Sometimes it's called the parallelogram rule of vector addition, or more commonly, you will see graphical vector addition referred to as tip-to-tail vector addition. Now, I call it graphical vector addition because it doesn't require any calculations. You're not going to be using any trigonometry, no sine functions or cosine functions or tangent functions. The only thing you would ever use is the Pythagorean theorem, so you could find the angle of a hypotenuse, because all your triangles will be right triangles, okay? But you won't actually solve for angles or anything, okay? So, but you will be able to answer some questions, which I'll show you in just a second. So here we have football players again, all right? They're going to stick together again, so this is going to be another perfectly inelastic collision, but they're not coming head on like we saw them in the previous lecture video. They're coming in at right angles, okay? Now, as before, we have a more massive player, right, and a less massive player, so they have different momentums. They also might have different velocities. We're not given, we're actually just given their values of momentum, okay? So to find their final momentum afterwards, we acknowledge that it's conserved. So whatever is their initial momentum must be their final momentum once they're joined together, okay? How do we find the initial momentum? We add the vectors together, okay? When you add vectors together, you take one and then you place the other one so that the tail of the second vector touches the tip of the first vector. That's called tip to tail vector addition. And that's what we've done here. We've put the tip of P1 touching the tail of P2, forming a right triangle because conveniently, one is completely horizontal, the other is completely vertical. So then the hypotenuse is the total momentum of the system. That would be the initial momentum of the system and the final momentum because it doesn't change, it's conserved. And we could find this value of 583 by simply doing the Pythagorean theorem where you take the square root of 500 squared plus 300 squared and you'll get 583, okay, approximately. Right? So the larger initial momentum has a larger effect on the final direction of motion, all right? So afterwards, they will be moving in this direction. They show the angle here. That's great. Take note of it, right? It's not 45 degrees. It's not 45 degrees because these two vectors are not equal length. That's the only time you're going to get 45 degrees. You could solve for this with a inverse tangent function, but just trust me, it's 31 degrees. But what they mean here by the larger effect is that this triangle is dominated by the longer side, right? It's not like a symmetric 45 degree angle right triangle. Okay, it's got one longer side, and that's how you know what angle they'll be traveling at. This is the type of thing they actually will analyze in looking at the skid marks after a crash of cars. Okay, now here's a concept question on that very idea, because as far as this two-dimensional vector addition of momentum vectors goes, you're really just going to be responsible for answering concept questions like this one and the next one. Two lumps of clay of equal mass are traveling at right angles with equal speeds as shown. Okay? So this is a case where everything's equal, right? Unlike the football players, V1, V2, and M1 and M2 equal each other. So if I was to draw P vectors, which is momentum vectors, would they also have the same length? You betcha. All right? So is it possible that their final velocity is the one showing? Look carefully at that. This isn't just some messy sketch. Look, what do you notice about V3? How does it point? How big is it? Is this a possible situation for a perfectly inelastic collision? Okay? Yes, some energy is lost. We're not going to quantify that. We just care, do the vectors check out? No, not at all. Because if you actually did tip-to-tail vector addition, you'd end up with a momentum vector that's pointing at exactly 45 degrees, right? If the momentum vector is pointing at exactly 45 degrees, so is the final velocity vector, right? Because the two clumps are going to move as one thing, and the velocity of one object is always parallel to its momentum. It can't be any other way. It's just mass times velocity after all. Mass is a scalar, velocity is a vector, right? Does this angle, does this vector look like it's pointing 45 degrees relative to, the horizontal or relative to the vertical? Not at all, right? It's mostly horizontal, right? So no, this is an impossible figure. It is not physically accurate. Okay? What about this one? Right? Here we're not going to ask if the figure's right, we're going to ask to interpret it. This is like the forensics of a car accident. Two cars of equal mass collide at right angles to one another in an intersection. The direction of motion after the collision is shown, okay? Now this is going to be another case, we're assuming it's perfectly inelastic, they didn't bounce off of each other, they just crumpled together and moved as one, okay? Which car had the greatest velocity before the collision? Look at the way V points. It's definitely not pointing at 45 degrees. So it's not a trick question where you can say that they're going to have equal ones. Okay, so it's not C. Which one is it? Got your answer? Well, right, it's A for sure, right? Because look, the final velocity vector parallel to the net momentum vector, whether initial or final, because it never changed, right? It's pointing more in the horizontal direction. A was the car traveling in the horizontal direction. That means the motion of car A dominated the net momentum vector. Well, that means it was moving faster. Right? Now, it could be just because it was a more massive car, except we were told it's not. We were told that the cars have equal mass. There you go. All right. Now, this is a really fascinating set of concept questions. I'm going to leave them for you to do on your own, but it really makes you think about the idea of internal forces and external forces. So if you want to test your understanding and make sure that that idea of internal, external, and really what is the system and what's outside the system that I've mentioned many times, especially in this video, right? Because we've been kind of increasing the ideas, right? Building on ideas. And we got all the definitions out of the way in the last video, but on momentum, right? So, but the point being is that these are going to be some great concept questions to test your understanding. Thinking about this, as you can see up front, strange situation of having a fan and a sail on a boat, right? What does that mean? How would that work? Would it work, right? So, go through these, see if you if they make sense to you, or if you really feel like you need more practice on understanding external forces and internal forces, then probably review first and come back to this, right? But if you want to test your understanding on them and you think you have a good handle on what I mean by an internal force versus an external force, well, then here you go. Okay, all right. And there we are. We got to a good natural stopping point. I didn't do any handwritten examples this time, but there were some good numerical ones in the slides. I hope this second of 2 videos on the topic of momentum has been both interesting and informative. And the next lecture video on Chapter 8 is going to be all about rotation, which is good because I keep talking about it and we'll finally be able to define it. Bye for now.